In this video, we're just going to summarize what we've been talking about in terms of alkylation of enolates. So we've seen a few different approaches to be able to alkylate an enolate. Direct alkylation is the shortest way, and it could be the most efficient for some targets, but there are some potential challenges. Acetoacetic ester synthesis is based on a beta ketoester, and the malonic ester synthesis is based on a beta diester. Both of these are longer approaches, but in some cases it might be an advantage over direct alkylation. So with direct alkylation, you need to be careful of the base that is chosen to generate the enolate. You want to make sure that you have essentially complete conversion to the enolate, so a very strong base such as LDA is usually required. Keep in mind, you still don't really want to do this with aldehydes. There are other reactions that can compete, and you typically don't want to do direct alkylation when it comes to asymmetric ketones. But direct alkylation can be useful when it comes to symmetric ketones, esters, and nitriles. With the acetoacetic ester synthesis, you are using a beta ketoester that looks like this. This is acetoacetic ester itself, but really it can be any beta keto ester that is used as a starting material. And the advantage is that you have this position that is alpha to both carbonyls, and this can be alkylated selectively. If you are using the actual acetoacetic ester, then the way you can think of this is if you had acetone and you wanted to substitute one or more of these hydrogens with some alkyl group, then you could use the acetoacetic ester synthesis. So maybe you have an R group and an R prime. With this approach, you're not limited, though, to this particular type of compound. For example, you could start with a different beta keto ester. Let's say if we started with this. So we have some R prime, and that means that our final product would look like this. Well, now let's call this R double prime and R triple prime. So by using this derived from a beta keto ester, this is a way that you can install one or more alkyl groups onto this type of framework. So rather than actually starting with acetone or actually starting with a methyl ketone, you're using a beta keto ester as a substitute for it. You're using a synthetic equivalent, which gives you access to other target molecules. Now with a malonic ester synthesis, here you are using malonic ester. And once again, you can carry out one or more alkylations. The overall transformation is as if you have acetic acid and you want to replace one or more of these hydrogens with different alkyl groups. So another way to think about this is if you have a particular carboxylic acid that is a target, then you can think about making it through the malonic ester synthesis, where you can install one or two different alkyl groups. At this point, it's important to get practice, right? Look at some different synthetic approaches, think about different targets, and try to determine when a particular target can be obtained by direct alkylation, when a particular target is better accessed by the acetoacetic ester synthesis, and when a particular target is best accessed by the malonic ester synthesis.